So I was talking about capillaries, and in that capillary video, because they only let you watch around about 3 minutes of it, I was then going on and talking about sinusoidal waves in rectifiers. And how we rectify alternating currents into direct currents, and how we can use capillary tubes to generate electricity, and perpetual motion, and loads of stuff. Right, so what I was getting at was this top one here. Right, this is an alternating current. So you've got 0 volts here, and you've got 0 volts here, yeah? And we go from minus 17 volts to plus 17 volts, to minus 17 volts to plus 17 volts, to minus 17 volts to plus 17 volts. And that's alternating current, so that's a 17 volt alternating current. And then how we rectify that into a direct current, and just take the bottom bits off, just take these bottom bits off underneath the line. What we do is we use a rectifier, and when the current drops below 0 and goes into a negative, the rectifier is full of diodes, and diodes are like a one-way tap. They'll only let positive energy come through. When it goes negative, it puts a block up. When it goes positive, it lets go through. It's like a one-way tap. It only lets electricity flow in one direction. The alternating current, it's both directions. Rectified electricity, direct current, only flows in one direction, and that's what we want. It's miles more accurate. This is what we need. So what they do is, this is a representation of the start of a dynamo. Yeah, that's a dynamo current, and this is what happens in the alternator. You get the first bit of electricity, which is from 0 to 17 volts, and it lets all that go through that side. Yeah? What we have is, instead of one set of windings in the dynamo, we have 3 sets of windings. Yeah? And the link to each part of this rectifier here. Alright, one set onto that one set onto that one, and one set onto that one. And then the positive energy from the first set gets pushed out. Yeah? And when it turns to negative, when it comes up to this end bit here and starts going out there, it just blocks it. Yeah? And by that time, the second one's already started charging, like, yeah? So then the positive energy from the second one is pushed out all the way through, and then when the third one starts charging, the first one's just about stopped, and it is the design, so it's when it starts, it stops, and so the positive energy starts coming out of the third one and is pushed out, and that's what you get in an alternator. Alright, that's alternating current into direct current. That's what we do. Very, very easy, and this is what was explained to me at college. So I've got capillary action, I've got rectification, I've got regulation, I've got many more things as well, but these are the simple things which led me to thinking, well, hang on a second, if I'm taking that and wasting that, so I'm wasting that negative energy there, I'm taking half of the energy and going alright, and if I do that, which I am doing, because that's what we do, we just chuck half the electricity away, we put 3 times the amount in, and then take half of it away, and take half of it away. Yeah? So it's 3 times. It's 3 steps forward, 1.5 steps back. 3 steps forward, 1.5 steps back. 3 steps forward, 1.5 steps back. Alright, that's what's happening. So if we go 3 steps forward, take the other bits that are negative. 3 steps forward. 3 steps forward, 3 steps forward, 3 steps forward, it's then perpetual, there's no doubt about it, absolutely no doubt about it whatsoever. We are just chucking half of our power away in every single circuit. Alternating current, chucking half of it away. Direct current, chucking half of it away. That means all that oil that you've just burnt to make this ultra efficient digital camera work, which is really efficient now and uses not any electricity at all, half the energy that it takes to power that is just waste. So if you say you're 97% efficient now with a fission reactor, you're not, are you? You're 45%, 46% efficient, aren't you? And if you are actually 97% of efficiency and you're chucking half away, that means you're around about 100 nearly 200% efficiency now. We're well over Unity. Well over Unity now. Well over Unity now. Now all we've got to do is when you get this battery and you put a wire from there round to a consumer and put it back into there, like, yeah, what happens is you get all the electrons flowing from the positive side to the negative side, yeah, and it's like they envision it like, let's say let's imagine two of these batteries now. Let's imagine that was the one battery. You've got the positive side and the negative side. What happens is you fill up the positive, yeah, and you put a wire onto the negative, but you put a consumer in there, yeah. If you put the direct to there, like that to there, it just bang, all the energy will go straight away, and the whole thing will go pfft, wires will melt and everything. So we put a consumer in there, like an electric motor or something, and the electricity flows from the positive, which is higher than the negative, down to the negative. No, it can be the other way around. It can be the positive can be lower and the negative can be higher. It just flows straight to it, yeah. Doesn't matter which one's higher, which one's lower. Just got to know that there's more in the positive than there is in the negative. And electrons, yeah. So the electrons flow from the positive to the negative, and while they're flowing, we use that flow to make something work. Yes. But what we don't do is what we've done is, like, yeah, you've got this electron flow, and the electron flow has got energy in it, so we say, alright? And as it flows from A to B through C, we forget about E. We just completely go, there's E, chuck it away. Just forget about E and don't worry about it. We don't just waste it. Waste. Because on the way from A to B through C, that flow through C is making C do something. It's giving C some effort because of the flow. And then C produces, let's say it's an electric motor, C then pumps some water up a hill. And then after the batteries are flat, we recharge them, don't we? Yeah? But what you can actually do is, you've got the flow, right? Just forget all the A, B and C, you've got the flow of current. And that's what's creating the effort in the electric motor. But the wires are full of this as well. And they get hot. Really fucking hot, because there's all this flow going through them. So you have to do bigger and bigger. The bigger the wire, the less resistance, so the more flow you can get through. But we don't do anything with that flow. We just allow the motor to take the flow. Now if we coiled more copper around the outside of the wire, we put another set of coils around that. Yeah? And not only that, if the wire that's going around, if we put a coil in it like this, if we put a coil into it and then let it go off like that, what happens then? We've already got that. We have electric, we have roll-up leads that you pull out, extension cords we call them, yeah. And you have that there. And what happens when you leave it all bunched up? The more current through, you get a lot of heat off it, don't you? Lots of heat. What can you do with heat? What does heat do? It heats things, doesn't it, eh? So for a start, you've got heat energy which you're just chucking away. You're not even using it. Yeah? But on top of that, you've got electron flow. Now how does an alternator work? You spin a magnet through a set of copper windings, and that makes the electrons flow, doesn't it? Yeah, it makes the electrons flow. Yeah, so electron flow, because you've got a magnetic field which is a load of electrons flowing, and you